Okay, so we'll do a quick little video here on one of the other types of reactions, which is called oxidation and reduction. So oxidation and reduction, we often sometimes abbreviate this as redox reactions. Okay, and the redox here, this comes from RED, read, not red. That comes from reduction. And then obviously the ox here is the oxidation part of this. Okay, these are very, very, very common types of reactions, and they actually encompass or incorporate many of the other types of reactions we've looked at previously. Now, we can look at reduction and oxidation from several different perspectives. The first one is by looking at the reactions in terms of electrons and what's happening to an atom as you go from the reactant side to the product side. So we define oxidation as the loss of electrons from an atom. And the thing you won't need to know about oxidation and reduction is that they are opposite processes. Okay, so that's key to understanding what's happening. So reduction and oxidation are opposite process. So if you know what one is, you can predict what the other one is going to be. It's just the opposite. So if oxidation is the loss of electrons, that means reduction then has to be the opposite of losing, which is gaining electrons. Sometimes you'll see this being abbreviated as OIL. So oil, oxidation is the loss of electrons. And then rig, reduction is the gain of electrons. So oil rig is a common mnemonic that is used to help us remember what this involves. Now, they both have to happen simultaneously. Okay, you can't have one without the other. Okay, they kind of go together like peanut butter and jelly, milk and cookies, peas and carrots. They have to, you can't have one happening. If something is losing electrons, those electrons have to go somewhere and they're gained by the thing that is undergoing reduction. So let's take a look at reduction oxidation in terms of electrons. So we can take a look, let's look at a slightly different example here to illustrate this. So if you, in terms of the electrons, right? So we said oxidation is the loss of electrons, and then reduction is the gain. Now, what impact does this have in terms of the charges of the species involved? Well, think about this. If you are gaining electrons, you're gaining negative charges, right? Electrons have negative charges. So whatever is undergoing reduction will become more negative. Okay, that's my abbreviation for negative, which means if something is losing electrons, then it will become the opposite of that, which would be more positive. Okay, because we're losing negative charges. So this has implications for what's known as the oxidation numbers. For the atoms or the species involved, right? So we may not be able to see the actual electrons being lost or gained, but we can look at things called oxidation numbers, which we often abbreviate as ON, or sometimes we call it oxidation states. They both mean the same thing, which we abbreviate as OS. And there are a couple of rules that dictate what's happening here. So let's take a look at an example. We'll do, for example, the rusting of iron. Okay, so iron, as we know, is Fe. So Fe, iron, which is a solid, can react with oxygen, O2 in the air, that's a gas, to produce the rust, which is iron oxide, Fe2O3. That's our solid. I'm not going to balance the equation just for simplicity's sake. We just want to illustrate how we determine oxidation numbers. So first rule for oxidation numbers is for an element, the oxidation number, so ON, oxidation number, is 0. So here I have my iron. It's an element, solid iron. Oxidation number will be 0. Here I have oxygen as an elemental form. Oxidation number is going to be 0, right? So that's the first thing. Second thing is for ions, oxidation number for ions is simply the charge. For our purpose, that's what we're going to assume that they are. Simply the charge on the ion. And the charge on one of those ions in the ionic compound. Okay, so here I have my iron oxide, right? That's an ionic compound. What's the charge on the iron? What's the charge on the oxide? Well, we know oxide is always -2, right? Oxygen always forms a -2 charge. And you can do your cross charge in reverse here to determine that the charge on the iron on each of these ions is +3. And that's the oxidation number that we have in both of these. And all we're doing is we're seeing now, does the oxidation number increase or does the oxidation number decrease? Does it become more positive? Does it become more negative? Well, let's just compare on both sides. Iron goes from 0 to +3. That's an increase in the oxidation number. Okay, so that would be an oxidation. So oxidation number increases, that's oxidation. And then guess what? Once you figure that out, well, then the other thing has to be the opposite, which would be reduction, which is there's a decrease in the case of oxygen. There's a decrease in the oxidation number, so that would be reduction. Okay, and that's what we're looking at. If you cannot see the electrons themselves, you can look at the oxidation numbers to determine whether one is occurring compared to the other one. Okay, let's take a look at a couple other examples, maybe one other example at least. If we have CH4 reacting with O2 to produce CO2 and H2O. Okay, so here we don't have ionic compounds, but we do have covalent ones, and we can still, apply some of the rules that we saw before. So some other rules that we're going to see is that the oxidation number for oxygen in a compound, as we saw previously, is usually -2, and then the oxidation number for hydrogen in a compound is usually +1, right? Unless, we don't see this very often, but unless it's combined with with a metal. So with these other two rules here, we can assign oxidation numbers. So here we have our oxygen in the elemental form, O2, so we know the oxidation number there has to be 0. If we look at oxygen on the other side, in both CO2 and H2O, now it's not in the elemental form. It is part of a compound. So here each O has to be -2, and that O in H2O is -2. Applying the other rule, so we know hydrogen is going to be +1. Each hydrogen is +1. And each hydrogen here in the CH4 is going to be +1 as well. So now we need to determine what the oxidation number of the carbon is in CH4 and CO2. Well, let's take a look at CH4. We're saying each hydrogen is +1, and we have 4 of them, right? So 4 times +1 will give me +4, which means the carbon then has to be -4, so that overall, this thing is 0, right? The CH4 overall has to have a 0 charge because it's a neutral compound. Same thing with CO2. If I know that each oxygen is -2 and I have 2 oxygens, that gives -4, which means the carbon now to cancel that out has to be +4. So I have my oxidation numbers assigned. All I'm doing now is comparing the oxidation numbers. So I can see carbon goes from -4 to +4. Okay, so carbon goes from -4 to positive. That's an increase in the oxidation number. So that would be oxidation. Okay, if I look at oxygen, oxygen goes from 0 to -2 in both of these cases. So I can then say, in the case of oxygen, okay, it goes from 0 to -2. That's a decrease. It becomes more negative. So decrease in the oxidation number, and that would be reduction. Okay, so that's how we can apply some of those rules to determine oxidation numbers. And then all we're doing is comparing the same atom on both sides of the equation. Is it becoming more positive? Is it an increase or a decrease in the oxidation number to determine one versus the other? The other things that we'll see later on down the road that allows us to determine oxidation versus reduction is um, the loss or gain of oxygens or hydrogens, right? So let me summarize this really quick. So we know that oxidation, and we have our reduction. So we saw that oxidation is the loss of electrons. Reduction would be the gain of electrons. Oxidation is an increase in the oxidation number. Reduction is a decrease in the oxidation number. And now the other things we'll look at are a little bit more obvious to determine whether something is oxidized or reduced. We don't always see these, but we're going to see them quite frequently. Oxidation is also the gain of oxygen. It kind of is in the name, right? Something is undergoing oxidation. We're adding O's, which means reduction would be the opposite, would be losing oxygen. Oxidation is also the loss of hydrogens, which means reduction would be the gain of hydrogens, right? And in some cases, it's a lot easier to see whether O's are being lost or gained, or whether H's are being lost or gained. In other cases, it's easier to see whether oxidation numbers are increasing or decreasing. So let's go back to the example that we had before, CH4 plus, whoops, plus O2 to give CO2 and H2O. So if you think about what's happening here, right, carbon going from the left side to the right side, it is losing hydrogens. So that would tell us that it's undergoing oxidation. Also, we're seeing that carbon is gaining oxygen, right? It loses the H and then it gains the O. So that confirms that it is undergoing oxidation as well. And we looked at the oxidation numbers on top and we determined that already. But now we're saying we can look at O's and H's to determine the same thing. If I look at the oxygen, for example, okay, the oxygen goes from being combined with itself to being combined with H now. So the O is gaining H. So if it's gaining H, that would be reduction. And if I look at my oxidation numbers on top here, we saw that the oxygen was a decrease in oxidation number. So that would confirm that it is reduction. So depending on what type of a reaction you're provided with and what you're specifically asked for, you can look at a variety of things to determine whether something is undergoing oxidation or whether it's undergoing reduction.